So in this video we are going to discuss about vector groups in three-phase transformers, and we will be discussing many things related to this particular topic, but let us just start our discussion with the question that why do we need to have so many vector groups? Well, in order to illustrate the answer of this question in a better way, I have just drawn so many sets of three-phase windings. Now, it is assumed that these three sets of windings are the windings of the high voltage side of a transformer, and this all four sets of three-phase windings are the low voltage winding of a transformer. Now, suppose that somebody says that the high voltage side of the transformer or the primary side of the transformer will be connected in star. So it is not difficult to form a star connection out of these three sets of windings, because we can simply join these three terminals, form a neutral, and it can be grounded. And if somebody says that the low voltage side of the transformer is connected in delta, then that is a very big concern, because how are we going to connect the delta is quite challenging, because we can connect delta in this way. So this is widely accepted delta connection and there is nothing wrong in it. But what if we connect delta in this way? So this is also widely accepted delta connection and there's nothing wrong in it. Both of these two windings are connected in delta, but both of them are quite different from each other. For this set of winding, let us just assume that we connect delta in this way, so we can see that it is similar to this one, but what we do is we are taking this as A phase, this as B phase, and this as C phase. So now it is different from this one. Now here what we do is we connect delta in this way, but here also we do the same thing. We are taking this as B phase, this as C phase, and this as A phase. So all of these four sets of three-phase windings are connected in delta, but all the four are quite different from each other. They are different in the sense that all four are going to have different phase angles. So what I mean to say is that let us just take this as the reference side, and if I am marking any electrical quantity for this particular phase, let's say it is A, so A can be either voltage or it can be current. And if I'm marking this as A at an angle of 0 degree, then for this particular drawing or for this particular connection, it will be small a at an angle of minus 30 degrees, and here it will be small a at an angle of plus 30 degrees. Similarly, for this winding, the phase angle will be something different, and here it will be different from all these three sets of windings. So we can see that we have a lot number of possibilities to make connections if it is a three-phase winding. So based on so many possibilities, we just group our transformers, or based on so many connections, we group our transformers into various vector groups. So just listing down the vector groups that we have. So listing down the vector groups, what all vector groups we have is, basically we are quite aware of vector group 0, we are aware of vector group 1, we are aware of vector group 6, and we are aware of vector group 11. But we just don't have only this much of vector group, but we have vector group right from 0 to 11. So we have vector group 0, we have 1, we have 2, we have 3, we have 4, we have 5, we have 6, we have 7, we have 8, we have 9, we have 10, and we have 11. And each of these vector group is going to introduce a different phase shift. So the amount of phase shift it is going to introduce is quite simple. In order to know that, what you have to do is we just have to multiply that vector group's number by minus 30. So if it is 0, we are going to multiply 0 by minus 30, and the resultant will be equal to 0 degree. If the vector group is 1, then amount of phase shift it is going to introduce on the secondary side of the transformer will be 1 into minus 30 degree, which is equal to minus 30 degrees. If the vector group is 5, then it is going to be 5 into minus 30 degrees, which is equal to minus 150 degrees. If it is 9, it is 9 into minus 30 degrees, which is equal to minus 270 degrees. And if it is 11, it is going to be minus 330 degrees. So minus 330 degrees is also equal to plus 30 degree. That's why for vector group 11 we say that it is leading by an angle of 30 degrees, and for vector group 1 we say it is lagging by an angle of minus 30 degrees. So if we are taking this as the reference angle for 1, the resultant will be here, and for 11 the resultant will be somewhere here. So if this is 0, this is going to be minus 30 degrees, and this is going to be plus 30 degrees. So we have so many vector groups, and these are all the phase shifts that they are going to introduce. But still, for each vector group we have certain constraints. So in order to know the constraint that we have while making the connections, we are going to group our vector groups into two categories, and the first one is even group and the second one is odd group. So the even group is the group that contains all the even numbers. So we have 0, we have 2, we have 4, 6, 8 and 10, and the odd is 1, 3, 5, 7, 9 and 11. So the constraint is that if the vector group of the transformer is even, then both the windings of the transformer shall be connected in same fashion. So if the primary side of the transformer is connected in star, then the secondary shall also be connected in star. That's why we have star star 0, we have delta delta 6, and we cannot have cross connection. So if the primary is connected in star, we cannot connect it in delta, means we cannot have star delta 6 or we cannot have star delta 0. So this is an invalid connection. So this is a constraint regarding the connection if the vector group is even, and vice versa is the case for the odd ones. So if the high voltage side is connected in star and if the vector group is odd, then the low voltage side of the transformer shall be connected in delta. So we have star delta 1 or we are having delta star 11. So these two are feasible connections, but we cannot have delta delta 1. So this is an invalid transformer connection. So this was about the basics of vector groups in three-phase transformers. Now I think we shall have a discussion on the way we are going to connect our transformer windings if it belongs to a particular vector group. Well, before that, let us just have a brief discussion on concept of polarities in transformers. We will be basically discussing about the concept of polarity in single phase transformers, and we can extend that concept to three phase. There's nothing wrong in it. So in order to understand that, I am just drawing two sets of transformer windings. One is primary winding and the other one is secondary winding, and we generally locate dots at these 2 points. So what this exactly means is that if the primary side is drawing current in this way and if we have a load at this point, then the secondary is going to circulate current in this way. So if we are measuring the value of current at this point, and if it is I at an angle of 0 degrees, here it is going to be I at an angle of 180 degrees, and this one will be plus, this one will be plus, and this one is going to be plus, this one will be plus. So for the reverse case, it will be something like if we have a dot at this point and if we have a dot at this point, and if it is connected to a load, if it is drawing current in this way, then this is going to supply current in this way. So if we are measuring current at this point and if it is I at an angle of 0 degree, here it will be equal to I at an angle of 180 degrees. So sorry, here it will be, I've written 180 degree, it is 0 degree only, because both of them are going to have same angles if the connection or if the location of dots is something like this, and it will be, if the dot is like this, then in that case we are going to have 180 degree phase shift. So how are we going to locate the polarity in a transformer is something for which we have to perform polarity test on the transformer. And how we perform the polarity test is, suppose we have two sets of windings and the windings are connected in this way. If the dot is located at this point and this point, and if it is 1:1 transformer, and if we are applying voltage from this side, and if the value of voltage is V, and we have to short these two terminals, and we are going to measure voltage at these 2 points with the help of a voltmeter, then what will be the value of voltmeter if the dots are located at this point? Then it's obvious that if this one is going to be positive, this one will be negative. At that time this one will be positive and this one is going to be negative, and the DC equivalent of this circuit will be something like we have a connection in this way. So it's obvious that this one will be V, this one will be V, and the resultant reading in voltmeter is V minus V. It will be equal to 0. If the voltage is not, or if the transformation ratio is not 1:1, then this one will be V1 and this one will be V2, and the resultant will be V1 minus V2. So it will not be 0, but it will be subtractive. But if the polarity is not located in this way, however the polarity was located, let's say the dot was here and here, and for the secondary side the dot was located at this point. So if we have a voltage and if we short these two terminals, and if we add a voltmeter at this point, and assuming that it is 1:1 transformer, then it's obvious that this one will be positive, this one will be negative, this one will be positive, this one will be negative, and the resultant DC equivalent will be something like this. So value of this voltage will be P and this one is going to be P. So the resultant reading of voltmeter is going to be P plus V, which is equal to 2 times V. So this is how we perform polarity tests in transformers. So at this point itself, let me just mention one thing which we will be assuming as we proceed on with our discussion regarding the connection of windings in for a particular vector group. And if it is something like this, and if I'm rotating this by 90 degrees in this direction and this winding by 90 degrees in this direction, then it's obvious that it is going to be something like this. The dot will be located at this point, and for this one the dot will be located at this point, and if this is drawing current in this way, it is going to draw, or it is going to supply load in this way. So this is the way the current flows in the transformer if the dots are located this way. On the nameplate of the transformer, we have an expression regarding the vector of the transformer, and it will be something like vector group, and it will be written like y and d5. Now there is some meaning regarding this expression. Well, it tells that, let us just suppose that we have a transformer, and this side is the HV side, and we are going to have three phases for that, and this side is the LT side, and we will be having three phases for that. So the capital letter of this expression, that is Yn, says that the high voltage side of the transformer is connected in star and it has neutral. So this side of the transformer is connected in star and it has this kind of winding configuration inside the transformer, and it has a neutral as well. Now the smaller letter of the expression, that is D, tells that the low voltage side of the transformer is connected in delta fashion. So this is connected in delta, and letter 5 says that this delta side lags the star side by an angle which is equal to 5 into minus 30, which is going to be minus 150 degrees. So if we have either voltage or current at this point, which is A at an angle of 0 degrees, here it is going to be A at an angle of minus 150 degrees. So this is what this expression exactly means. Now let us discuss how we are going to connect our windings for a particular vector group. So we have three sets of windings here and three sets of windings here, and let us suppose that on the nameplate of the transformer it is written something like this. So it's obvious that if this is the high voltage side, it is going to be connected in star fashion. So this is the way we are going to connect it. And regarding the polarity, as we have discussed, I am marking the polarity or dots at this point, and similarly the dots will be located at this point. And one says that here the phase angle will be minus 30 degrees if it is 0 at this point. Now considering the direction of flow of currents, we are having I for this phase, which will be I at an angle of 0 degrees. Here it will be I at an angle of 240 degrees, and here it is going to be I at an angle of 120 degrees. So since there is a flow of current in this winding, in order to balance that flow of current, we are going to have a flow of current in this winding as well. We are going to have a flow of current in this winding as well, and its direction will be something like this, and its angle will be 0 degrees. So I have just taken small I because the magnitude may not be the same, but the angle is going to be the same, and here it will be, and for this winding it will be something like small I at an angle of 240 degrees, and here it will be small I at an angle of 120 degrees. So now we have to connect this winding in such a way that at this point we are going to get an angle of minus 30 degrees. So now we are going to implement some basic mathematics, and it is like, suppose for the primary side we have these three equally spaced phases. So these are the three phases here, and we have A, we have phase B, and we have phase C. And on the secondary side of the transformer, if this one is at 0 degrees, the resultant shall have this direction, means it shall lag by an angle of minus 30 degrees. So in order to get a resultant of minus 30 degrees, what we are going to do is we are going to take minus of C. So if it is A minus C, then we are going to see that the resultant will be something like root 3 times of I at an angle of minus 30 degrees. Actually it will be small I at this point. So it is something like we have a connection of plus of A and minus of C. So as we have already said that if we have plus at all these 3 points, then this is going to be minus, so we are having minus at all these points. And similarly we have plus at this point, plus at this point, and plus at this point, and we have minus at this point, minus at this point, and minus at this point. So this is A phase, this is B phase, and this is C phase. So what we are going to do is we are going to connect positive of A. So what we are going to do is we are going to connect positive of A with negative of C. So this is positive of A, so we are going to take a point from this and we are going to connect it to negative of C. So this is negative of C. And similarly we can see that we have to connect negative of A with positive of B. So it is going to be something like this, and then it is going to be something like this. So the resultant connection is equivalent to y and t1, or we can just cross check it like this. So at this point we have a node, and here we can see that this current, that is I at an angle of 0 degrees, is getting divided into two parts. So the first part is this current, whose value is, we can find from here, it is I at an angle of 120 degrees. So the line current which is flowing in this line will be I at an angle of 0 degrees minus I at an angle of 120 degrees. So it's obvious that it is going to be root 3 times of I at an angle of minus 30 degrees. So this is how we are going to connect our Y and D1, or this is the winding configuration of our transformer whose vector group is Y and D1. Now if we take another example in which we have to connect the winding in fashion such as Y and D7, well, for that also we have to connect the star side of the transformer in this fashion. So this is how the neutral is formed, and for Y and D7 the phase lag will be nothing but minus 7 into 200 into 30, which is equal to minus 210 degrees. Well, for a phase shift of minus 210 degrees, it will be something like, if this is 0 degrees, 210 minus 210 will be somewhere in this direction. So for that, what you have to do, we have to take negative of A. If I am marking this as A, this as B, and this as C, I have to take negative of A, and the resultant with C is going to give something like this. So we can see that the resultant lags A by an angle of minus 210 degrees. So the resultant is nothing but it is positive of C and negative of A. So this is the positive of C and this is the negative of A. What we have to do, we just have to connect them in this way, and this is going to be the phase for our phase. So similarly, we are going to connect these two phases, and this is going to be for B phase and this is going to be for C phase, isn't it? And we can check it mathematically as well. So this is going to draw a current which is I at an angle of 0 degrees. This is going to draw a current which is I at an angle of 240 degrees, and this is going to draw a current which is I at an angle of 120 degrees. So here it is, in order to balance it, we have small I at an angle of 120 degrees, and in order to balance this current, it should draw current which is small I at an angle of 0 degrees. So it's obvious that here at this node, the current that is being fed to the load or being fed to the line, this line is nothing but it is I at an angle of 120 degrees minus I at an angle of 0 degrees, which is nothing but root 3 times I root 3 at an angle of minus 210 degrees. Similarly, we can check for other phases as well, but this is the connection which is equivalent, or this is how the windings of a transformer will be connected whose vector group is Y and D7. Similarly, if we take another example where it is YY8, then for YY8 the primary or the high voltage side of the transformer should be connected in star. It is going to have a neutral, so actually it is Y and 8, but I have just written it as YY8, and the secondary side should also be connected in star, but we have to give dot, and the dots will be located at this point. For this one, the dot will be located at this point, and the phase shift in the angle it is going to introduce will be nothing but minus 8 into 30, which is equal to minus 240 degrees. So if this is A and this is B and this is C, means if this is A, this is B and this is C, then for A phase it is going to be minus 240 degrees. So minus 240 degrees is nothing but this is going to be minus 240 degrees. Means for A, the phase corresponding to C on the secondary side will be the phase for A phase. So this is going to be the A phase. Then for B phase it is going to be minus 240 degrees. So this is going to be for B phase, and similarly this is going to be for C phase. So this is how the windings will be connected on the secondary side of the transformer if it is YY at an YY8. So now let us take an example in which we consider that the high voltage side of the transformer is connected in delta and low voltage side is connected in stars. So let us suppose that the vector of the transformer is D, Y and 1. So it's obvious that this side of the transformer will be connected in star. We are having a neutral. We are just marking the dots at these points, and here the dots will be located at these points. And here the current that is going out is, it's obvious that it will be small I at an angle of 0 degrees. Here it is small I at an angle of 240 degrees. Here it is small I at an angle of 120 degrees. Similarly, here also in the winding, the current will be I at an angle of 0 degrees. Let me just mark this one as capital I, and this is capital I at an angle of 240 degrees, and here it is going to be capital I at an angle of 120 degrees. So how are we going to connect the delta? Well, for that, let us take the three-phase balance system, and here it is capital A, capital B, capital C, that is A phase, B phase, and C phase, and it is connected in one fashion, or the vector of the transformer is one. So it's obvious that this side, if the angle is 0, then at this point it is going to be plus 30 degrees, because this side lags by an angle of minus 30 degrees. So if it is lagging by an angle of minus 30 degrees, it simply means that if it is 0 at this point, then this side it is going to be plus 30. So now what we are going to do is, let us just see how we are going to get a resultant of plus 30 degrees. Well, if it is 0 degrees, then plus 30 degrees will be somewhere here. So this is plus 30 degrees, and in order to get plus 30 degrees, what we are going to do is we are going to take negative of b. So it is simply a minus b, or it is plus of a and minus of b. So this is plus of a and this is minus of b. So we are going to have our connection in this way. Similarly, for this phase, the connection will be something like this, and this is going to be connected in this way. So this is the equivalent circuit, or this is the equivalent connection of a transformer whose vector group is dyn1. So this is how the windings of the transformer will be connected if the vector of the transformer is dyn1. And actually, in this case, or in all the cases that I have discussed, I have just taken only one phase, and based on symmetry I have applied for all the phases. But if anybody wants to check it, they can check, or they can apply it to other phases as well. They are going to get the similar connection. So the next topic that we are going to discuss is the vector group testing of the transformer. So suppose that we have a new transformer and we have no such idea about the vector of the transformer, or suppose that the transformer was dismantled and again it was reassembled, but we have no idea about the vector of the transformer, or there might be a possibility that the vector group got changed, because we can see that by a simple change in connections we have different vector groups. So how are we going to perform vector group test on the transformer? Well, for that, what we can do is, let us suppose that we have a transformer whose vector group is y and d1. So for y phase, I am taking this as the reference. This is A phase, this is B phase, and this is C phase, and this is the neutral, and this is the delta side. So this is A phase, this is B phase, and this is C phase. And since it is 1, it's obvious that it will be lagging by an angle of minus 30 degrees. So what we are going to do is we are going to rotate it by an angle of minus 30 degrees. So what we mean is that we are going to short this A and this A together. So actually I have written it as capital A and capital B and capital C. I'm going to mark it as small a, small b, and small c, in order to indicate that they are low voltage side of the transformer. So small c will be something like this. So if we short capital A with small a, the resultant will be something like this. This is capital A, small a, then we have small b, small c, and then we have capital B and capital C, and this is capital N. So now what we are going to do is we are going to apply three-phase balanced voltage across capital A, capital C, capital A, capital B, and capital C, capital B. So we are going to have three-phase application across all these three phases of the high voltage side of the transformer, and we are going to do the measurement. So what values we will be getting is, we will get that capital A and small b, that is this vector, plus small b and capital N, that is this vector, will be equal to capital A and capital N, that is the total vector, which we can clearly see that this is the value we are going to get. Apart from this, what result we are going to get is that capital C and small b, that is this vector, and that is capital B and small b, and capital C and small b are going to be approximately equal. Then what we are going to get is that this vector, that is capital C and small c, so capital C and small c is smaller than capital B and small b, so we can see that this vector is longer, so capital B and small c will be longer than capital C and small c. So if we are getting all these three values or these three results, then it means that the vector of the transformer is y and d1. Now suppose that the vector of the transformer is y and d11, then in that case it will be something like we have star in this way, and we have delta connection in this way. Now what we are going to do is, this is capital A, capital B and capital C, this is small a, small b and small c. Now what we are going to do is we are going to short A and A together. So if we are shorting them this way and the vector of the transformer is 11, what will happen is that it is going to shift by 30 degrees in this direction. So the resultant will be something like this. We have small b, small c, capital A, small a, then we have capital B and capital C, and this is going to be the neutral. So we can see that in this case, the result, if we are applying voltage across these all three phases, then the reading we will be getting will have some pattern like the voltage across capital A and small c and small c and capital N will be equal to capital A and capital N voltage. So voltage across capital A, small c plus small c and capital N will be equal to capital A and capital N voltage. Then we can see that capital C and small c and capital B and small b will be almost equal. So we have capital C, small c approximately equal to capital B and small c. And we can see that capital B and small b will be smaller than capital C and small b, because we can see that the vector length here is longer than the vector length compared to this one. So capital B and small b will be smaller than capital C and small c. So this is the result, or this is the pattern of result that we will be getting if the vector of the transformer is y and d11. So this is how we perform vector group test on three-phase transformers, and the same concept can be applied or implemented to other vector groups as well.